Welcome back, Calc students. This is tutorial number 2 based on section 1.3 exponential functions. I'm on the topic of growth and decay. So we just completed the first tutorial with some graphs of exponential, and now we're going to focus on applications of growth and decay. And because we're talking about real world applications, this K value is going to be positive. So this right here, the number in front of your base is going to be positive for the application of growth and decay. Going down to growth, A is going to be a value greater than 1, and decay, A is going to be between 0 and 1. We did talk about previously why it cannot equal 1, A, as well as A cannot equal 0. The previous example, I believe it was 2 to the x. That's going to be a growth model, exponential growth. And then if I have A that's going to be between 0 and 1, that would be something like this in our previous example, and which is really a half to the x, and that would be a decay type model. It looks like this. There we go. All right, so a couple of examples. The first one is decay. So half-life. Suppose the half-life of a certain radioactive substance is 20 days, and there are 5 grams present initially. When will there only be 1 gram of substance remaining? Okay, so initially our value, our K, is going to be 5. That is our initial. So let me just kind of set the stage on how we write our function here. So initially we have 5, and then it says something about half-life. So half-life, if I take half the substance, we're going to get 2.5, or 5 halves. And it takes 20 days to get there. So let me just, so I wonder what T would be to get us to 2.5. If I let T equal to 1, so if I just put a T right here, that's going to be day 1, and that would T would be a 1, and I'm going to get my 1/2. But that's not what it says. It says 20 days until you get half the substance. So I got it. Okay, so if I put a 2 in there, that's still not going to give me my half. Is going to be smaller than half the substance. So what we need to do is, if T was 20 days, that means I have to take this and divide by 20. So if I put 20 in for my X, or my T, then I get 20 over 20, and that would give me what my desired half-life. So if the half-life, they told you it took 10 days, then you take your exponent, divide by 10. If they told you it took 365 days to reach half-life, then you divide by 365. So our model for this application is 5 times 1/2 T divided by 20. And then the question is asking how much time would it take for 1 gram to be remaining. So you replace 1, your y, with 1, because that's the end result. And at this point, you got to solve for T. Now, because of the sequencing of the book, we talk about how to solve for exponents in section 5 of the chapter, which means you got to use logs to solve for exponents. So at this point, if you know how to solve for T algebraically using logs, go ahead. But ideally, they're looking for you to use your calculator. So I'm using Desmos here as an illustration. You can plug in your model, and then plug in what your y is going to be a 1, and find the intersection, and that's going to be how many days that it took. Okay, I'm going to move on to the second application. Suppose that a colony of bacteria starts with 1 bacterium and doubles in number in every half hour. How many bacteria will the colony contain at the end of 24 hours? Okay, well, let's just do a little table to model this colony of bacteria. So when hours is 0, you have 1. And then when it's a half hour, it's going to double. And then another half hour, 4. And then 3 halves, double 4, you get 8. Then you get your 2 hours, and it's going to be 16. And then you get your 5 halves, you get your 32. just so that you guys can see some patterns here. If I have my algebra students, I'd start at the bottom of the table and try to find some patterns. And this looks like it's going to be 2 times 2 times 2 times 2 times 2, 4 times 8, and there's going to be a bunch of 2's, and it's 2 to the 5th. 16 is 2 times 2 times 2 times 2, 2 to the 4th, and I think you guys are seeing the pattern here. And put 2 to the 0. Oops, I should have put that right there. That's going to be 2 to the 0. Okay. So this is the pattern that we have, and you can kind of come up with this. The model is going to be y equals 2 to the x or t, or however you want to write your variable. Now there is a 1. It does start with initially 1, and I could put a 1 in, 1 times that base number to the t. However, does this make sense? I don't know if this model is going to make sense. If I plug in, let's see, if I plug in a 2 right here, I get 2 squared, and that's 4. I'm supposed to get 16. Well, let's plug in a 1. If I plug a 1 in for t, I'm going to get a 2 to the 1st, but I need a 4. I need a 4. So what we need to incorporate is 2 times t, and let's see if this is going to work here. So if I plug in a 1, I'm going to get 2 times 1 as a 2, so 2 squared is 4. Good. I plug a 2 in, I'm going to get 2 times 2 is 4. Raise that to the 4th power, and that is 16. I'll try one of these fractions here. Let's try 5 halves. So if I put 2 raised to the 2 times 5 halves, yeah, I'm going to get this 2 to the 5th, and that's going to be 32. So this is our model right here. And the question is, how many bacteria will the colony contain at the end of 24 hours? Well, they want you to replace t with 24. And I'm not going to write out the value, except maybe I'll just write down 2 to the 48 bacteria. Okay, I'm going to stop this tutorial, and I will pick up the next tutorial with personal banking, and that will conclude growth and decay for now.